Welcome everyone. Thank you for taking the time to watch this presentation. Over the next 10 minutes, I will present research conducted in Trinity College Dublin with the support of the Irish Research Council and presented at the IEEE Systems, Man and Cybernetics Conference 2021, entitled Using Tactile Sensing to Improve Performance when Grasping Moving Objects. Robotic grasping has been very effective in changing many manufacturing processes and assembly lines. These applications are particularly well suited for robotic grasping because of the structured nature of the process and the environment. However, there is an increasing demand to deploy robots in more unstructured environments. This includes applications like deploying mobile service robots in hospitals and homes, but even factories and assembly lines, which were historically very structured, are becoming less so with the emergence of flexible manufacturing. An essential part of enabling a robot to be an effective solution in these applications, and many more, is the ability to interact with dynamic objects. In this research, we focus specifically on one aspect of interacting with dynamic objects, that is, grasping a ball which is traveling towards the gripper. The typical approach to addressing this problem, as seen in examples from the literature, relies on estimating a point of interception, this being a position and time at which the robot estimates that it will be able to intercept the moving object. In this research, we refer to this as the estimate-only strategy. It can generally be simplified into 3 steps: sense, plan, and act. First, vision sensors, both on the robot and in the environment, detect the object. At this point, an object's state is determined, including a position and velocity vector. Next, there is a planning stage, where the sensor data is used to model the movement of the object and calculate an appropriate position and time for the robot to intercept. The most common strategy used in this step for catching a ball is fitting a parabolic path to the velocity vector and choosing a point along the trajectory of the ball which passes through the graspable range of the gripper. Different examples have taken different approaches to this, some choosing to intercept the ball as early as possible, while others consider factors such as interception speed, joint limits, and acceleration. The commonality between these examples, however, is that they all calculate a position and time at which they will attempt to catch the object. Finally, the act stage involves moving the gripper into the estimated interception position and executing the grasp at the estimated time. These 3 steps, sense, plan, and act, are typically executed in a loop until the grasp is attempted. The estimated interception position and time are constantly updated with new sensor data, giving a more accurate estimate. An issue which arises from this strategy is the high computational overhead associated with processing image sensor data and modeling the trajectory of the object. The result of this is a latency between acquiring the sensor data and acting upon it. Therefore, there comes a point at which the object is too close to the gripper for any sensor data collected to be processed in time to react to errors in the interception and attempt to mitigate them. Furthermore, when deployed in a real-world, unstructured environment, there are many sources of error which can lead to a non-optimal estimated interception position and time. An over-reliance on vision sensing is particularly problematic in an unstructured environment where noisy sensors, occlusion, and imperfect lighting conditions can be expected. Likewise, unstructured environments often result in difficult to model physics and incomplete models of both the world and the object, increasing the difficulty of accurately modeling the future trajectory of the object. Finally, not only can the estimated interception be non-optimal, but moving a real-world gripper into that position can also be prone to errors. For example, manipulators are typically long, open kinematic chains, which can lead to error propagation, whereby a small error in each joint can lead to a larger error in the final position of the gripper. Finally, moving the end effector into the interception position in the very short period of time before the object has passed by the robot and is out of reach can be difficult. But moving a large mass like a robot manipulator into position quickly can also lead to control problems like overshoot. All this contributes to an offset, both in space and time, between an optimal grasp and the attempted grasp. This research is concerned with the performance of two grasping strategies under a range of these offset conditions. Greater performance, even with the induced offsets from optimum, strongly suggest a strategy which will enable a robot to operate more effectively in unstructured environments. This research hypothesized that using a reactive control strategy based on tactile sensing in the fingertips would lead to improved performance and robustness across a wider range of grasping conditions. We've already talked about the estimate-only grasping strategy. Next, we need to talk about the proposed strategy, which we hypothesize will be more robust to offsets from optimum, and we call the reactive grasping strategy. This strategy is based on three simple rules. The grasp is triggered when the ball first makes contact with the tactile sensors. Upon detection of contact with an object, the gripper moves laterally so as to reduce the spatial offset and center the object in the gripper. The closing motion of the finger that first comes into contact with the object is delayed relative to the other finger. In order to compare these strategies, a test was designed and conducted in simulation. A two-finger pincer gripper would attempt to grasp a ball rolling towards it on a horizontal surface. The speed and position of the ball, as well as the timing of the grasp, could all be carefully controlled. In this way, the performance of each strategy could be quantified at a range of different error conditions, both spatial and temporal, and a range of speeds. The simulations were carried out in Gazebo and the control in RAWS. The simulated gripper is a two-finger under-actuated gripper. Each finger has 3 flanges, 3 revolute joints, and 3 tactile sensors. When the trajectory of the ball is aligned with the center of the gripper, it is considered optimal, and therefore has 0 spatial offset. From this, we induce spatial offsets to test the robustness of each strategy to errors in the interception position. 6 induced errors to the right and 6 to the left, for 13 total test conditions. We also examine the effect of offsets from optimum in the estimated interception time, by varying the time at which the grasp was initiated. Unlike spatial error, it is not immediately apparent what the optimum time to initiate the grasp is. We determine this empirically. A series of tests were conducted at a range of speeds and spatial offsets, and the grasp timing which yielded the highest average grasping success rate was defined as the optimum time to initiate the grasp. This was determined to be 0.17 seconds before collision. From this, we induced 2 temporal errors for testing, 0.3 seconds before collision and 0.04 seconds before collision. These are equidistant either side of the optimum. This video shows the reactive grasping strategy successfully grasping a ball with an induced spatial error. First, the ball is set in motion. Next, the ball makes contact with the gripper, which then attempts to grasp. This includes responding to the offsets from optimum in the interception by moving laterally and adapting the closing motion of the fingers. Finally, the simulation will run a test to determine if the grasp was successful. This involves raising the gripper off the ground plane to determine if the gripper can support the weight of the ball in the absence of all other supporting forces. The results are best demonstrated when organized into 3 graphs, one for each of the test speeds. The x-axis of these graphs show the spatial offsets and the y-axis the average grasping success rate. We can start by looking more closely at the data from the tests with the lowest object speed. The solid green trend line here represents the reactive strategy, while the dotted lines show the estimate-only strategy at the 3 different grasp times tested. In a trend we will see echoed in the graphs for other test speeds, the reactive strategy performs significantly better across a wider range of spatial offsets. We can also see a huge disparity in how performance deteriorates with positive temporal offsets versus negative temporal offsets. This graph would suggest that the impact of temporal offsets on grasping success rate is not symmetrical around the optimum. It can be seen that while one induced offset almost matches the performance of the estimate-only optimally timed grasp, the performance of the other drops below 10% across the entire range of tested spatial offsets. This highlights a further advantage of the reactive strategy, which is not subject to errors in the estimated interception, but instead its grasp timing relies on real-time tactile sensor stimulus. The results of the next test speed tells a very similar story, with the reactive strategy proving significantly more robust to offsets from the optimum interception position. We can see in this case that the reactive strategy's ability to mitigate the effect of the offsets from optimum is slightly lessened at this higher speed. Finally, this shows the highest test speed, and while we still see the features we discussed previously, we begin to see a few new ones. One notable feature is the drop in the success rate at low spatial offsets. This was attributed to a flaw in our proposed reactive grasping strategy. The strategy would move laterally so as to reduce the distance between the center of the gripper and the initial point of contact. Results presented up until now have shown this to be a very effective strategy. However, at this particular offset and speed, it performs non-optimally. In this situation, the ball rebounds across the center line of the gripper, meaning that the lateral motion of the reactive grasping strategy tends to move the center of the gripper away from the ball's current position and lowers the grasping success rate. This highlights an area of future research, which is to conduct a series of experiments to determine the effect which the density of tactile sensors has on grasp robustness. High-density tactile sensors should allow the gripper to better adapt to specific offsets, like this low spatial offset. Another aspect of this grasp worth noting is the performance of the estimate-only strategy when temporal offsets are induced. Where in previous graphs the speed was sufficiently low to allow the performance of the grasp with the negative temporal offset to achieve results which were very similar to the optimum grasp timing, at this speed, both induced temporal offsets cause the performance to drop dramatically. In conclusion, results show that the estimate-only strategy performs well at low offsets from optimum, but the performance deteriorates with larger induced offsets. In contrast, the reactive strategy matches the performance of the estimate-only strategy at low offsets, but continues to perform well at larger induced offsets. Finally, the reactive grasping strategy is able to adapt to errors in the interception and mitigate their effects in a way which is not possible for the estimate-only strategy, resulting in higher grasp robustness.